Regression gives us a disciplined language for asking how an economic outcome changes with an explanatory variable, while staying honest about uncertainty and the other forces that remain outside the model. Let us begin with a simple question. How does household food expenditure change as income rises? That question will help us distinguish description, prediction, and causal interpretation before we calculate a single coefficient. Regression supports much more than drawing a line through a cloud of points. In finance, it underlies asset pricing, portfolio risk analysis, and tests of market efficiency. In economics, it helps us study output, inflation, wages, trade, and policy. A regression can support explanation or forecasting, but only when its purpose, assumptions, and limitations are stated clearly. A useful research question names an outcome, an explanatory variable, a population, and the comparison of interest. Asking whether household income predicts food expenditure is more precise than asking whether income matters. Asking for a causal income effect is more demanding still because it requires a design that isolates income changes from preferences, household composition, prices, and other confounding influences. A credible project starts with a precise question and an economic reason to expect a relationship. From there, I want us to look hard at the data first, checking its quality, its missing values, its outliers, the units, and any transformations we might need. Only then do we choose the outcome. Pick the explanatory variables, state our hypotheses, and estimate the model. Diagnostics come before interpretation, never after, and we save any forecast or counterfactual claim until we understand what the fitted model can actually support. The simple linear regression model describes an outcome called y using one explanatory variable called x. We say that y equals beta 0 plus beta 1 times x plus an error term called u. Beta 0 is the intercept. Beta 1 is the slope. The error collects all determinants of y that are not represented by x. Under a correctly specified conditional mean, beta 0 is the expected value of y when x is 0. Beta 1 is the change in the expected value of y associated with a 1-unit increase in x. The phrase expected value matters. Individual outcomes need not lie on the regression line because each observation also contains its own unobserved error. The intercept can be mathematically necessary but economically uninteresting. If 0 lies far outside the observed range of x, beta 0 describes an extrapolation rather than a realistic case. We should not force a substantive interpretation on it. The slope is also local to the chosen units, so changing pounds to kilograms changes its numerical value without changing the underlying fitted relationship. Econometricians use several names for the same roles. X may be called an explanatory variable, predictor, regressor, or control. Y may be called the dependent variable, response, or regressand. These labels do not establish causality. Calling x an independent variable does not prove that changing x would cause y to change. Consider a financial example. A simple regression of a stock return on a market return can summarize the stock's market exposure. The slope is commonly called its market beta. The model can describe co-movement and support risk measurement. A causal interpretation would require an additional research design because many market forces affect both returns at the same time. The word regression has a historical origin in work on heights across generations. Very tall parents tended to have tall children, but the children were usually closer to the population average. A similar pattern appeared for very short parents. Today, regression is a general method for studying conditional relationships, not a claim that every variable must move toward its mean. Practical learning is easier with accessible data, provides built-in data for small examples, and packages connect us to macroeconomic and financial series. The important habit is reproducibility. A reader should be able to identify the data source, repeat each transformation, estimate the same model, and understand why a variable was included. Our first formal requirement is linearity in the parameters. For observation I, we say that y for observation I equals beta 0 plus beta 1 times x for observation I plus u for observation I. Linearity does not mean every point lies on one line. It means the conditional mean is represented by a line with a common intercept and slope. The central exogeneity condition is zero conditional mean. It says that the expected value of the error, given x, is 0. Equivalently, the conditional expected value of y equals beta 0 plus beta 1 times x. This condition links the fitted relationship to the population parameter that we want to learn. Zero conditional mean can fail when an omitted determinant of y is systematically related to x. For example, a wage regression using education alone may place ability, family background, or local opportunity in the error. If those factors are related to education, the estimated education slope mixes several channels. More observations do not automatically repair this specification problem. Homoskedasticity means that the conditional variance of the error is the same at every value of x. In plain language, the vertical spread around the regression line remains constant. This assumption is useful for the classical standard error formula, but economic data often violate it. Household expenditure, firm size, and income data commonly show a spread that grows with scale. Another classical condition says that errors from different observations are uncorrelated. One observation's unexplained component should have no linear association with another's. This may be reasonable for a carefully sampled cross-section, but it is often implausible for time series, spatial data, or observations within the same firm, country, school, or household. Normality is optional for the basic unbiasedness and consistency arguments. If the conditional error follows a normal distribution with mean 0 and constant variance, exact small sample t and f inference becomes available. In large samples, approximate inference can often rely on other results. Treating normality as essential to ordinary least squares estimation is therefore a common mistake. Independence is stronger than zero covariance. To see why, imagine a symmetric variable x with mean 0 and let y be x squared. Y is completely determined by x, so the variables are dependent. Yet their covariance can be 0 because positive and negative values of x cancel in the relevant average. A zero covariance statement therefore describes only linear association. These assumptions play different roles. Linearity and zero conditional mean identify the conditional relationship. Constant variance and uncorrelated errors support the familiar efficiency and standard error formulas. Normality supports exact finite sample distributions. Good practice asks which conclusion uses which assumption, instead of treating the assumptions as one indivisible checklist. Different problems call for different fixes, and I will take them up one at a time in the lessons ahead. If the relationship is nonlinear, we transform a variable or enrich the specification. If the error variance changes, we use robust inference or careful weighting. If errors are correlated, we need a covariance estimator that captures that dependence. Endogeneity is the deepest problem, and it usually needs controls, instruments, panel methods, or a research design that creates exogenous variation. Here is the warning I want to leave you with. A regression equation is not yet an empirical result, and a fitted association is not automatically a causal effect. To get there, we need a defensible question, suitable data, a meaningful specification, and diagnostics match to how the data are actually structured. In the next lesson, let's turn this model into an estimator using ordinary least squares. Suppose we observe many pairs of x and y. Any two distinct points can define a line, but a sample usually contains far more than two observations, and no line passes through them all. We need an explicit rule for choosing among possible lines. Ordinary least squares, or OLS, chooses the line that makes the observed outcomes collectively as close as possible to their fitted values. For each candidate intercept and slope, we calculate a prediction error for every observation. We square those errors and add them. OLS selects beta 0 and beta 1 to minimize that sum. Squaring prevents positive and negative errors from cancelling, gives extra weight to large misses, and produces a smooth optimization problem with a convenient solution. The use of squares is powerful but not neutral. A very unusual observation can contribute disproportionately to the objective, so least squares may be sensitive to outliers. This is one reason that a regression table should always be accompanied by graphical and influence diagnostics. The optimization rule finds the best line under its criterion, not necessarily the best scientific model. The slope estimate can be described as the sample co-movement between x and y divided by the sample variation in x. More precisely, beta 1 hat equals the sum of centered x times centered y divided by the sum of squared centered x. The intercept estimate equals the sample mean of y minus beta 1 hat times the sample mean of x. This formula explains two essential facts. First, we cannot estimate a slope if x has no sample variation. Second, the sign of the slope follows the sign of the sample co-movement between x and y. The fitted line can be written as the mean of y plus beta 1 hat times x minus the mean of x, so it passes through the sample mean point. For observation I, the fitted value is beta 0 hat plus beta 1 hat times x for observation I. The residual is observed y minus that fitted value. Residuals are therefore observable after estimation. They provide a sample-based picture of what the fitted conditional mean leaves unexplained. With an intercept in the model, OLS residuals sum to 0. They are also orthogonal to x, meaning that the sum of x times the residual is 0. Fitted values are orthogonal to residuals as well. These properties follow from the first-order conditions that minimize the sum of squared residuals. Orthogonality must not be confused with model validity. OLS mechanically makes the sample covariance between included regressors and residuals equal to 0. It does not prove that the population error is unrelated to x. An omitted variable can bias the slope, even though the fitted residuals satisfy every OLS normal equation exactly. An error and a residual are different objects. The error is the gap between an outcome and the unknown population regression line, so we cannot observe it directly. The residual is the gap between the outcome and the estimated line. We use residuals to investigate variance patterns, dependence, outliers, and functional form, while remembering that they only approximate the errors. Estimates vary from sample to sample, so a coefficient needs a measure of uncertainty. To test whether a population coefficient equals a proposed value, we take the estimate minus that value and divide by its estimated standard error. The result is the t-statistic. For the common null hypothesis of 0, the numerator is simply the estimated coefficient. Under the classical assumptions with normal errors, the simple regression t-statistic follows a t-distribution with the sample size minus 2 degrees of freedom. The t-distribution has heavier tails than a standard normal distribution because the error variance is estimated. As the degrees of freedom increase, this extra uncertainty shrinks and the two distributions become increasingly similar. A large absolute t-statistic indicates that the estimate is many standard errors away from the null value. The p-value reports how unusual such a statistic would be if the null hypothesis were true. Statistical significance is not the same as economic importance. A tiny effect can be precisely estimated, while an important effect can remain uncertain in a small or noisy sample. A confidence interval presents the same uncertainty in a more informative scale. It contains coefficient values that are not rejected by the corresponding two-sided test. Its width reflects both the estimated noise and the variation in x. A narrow interval can support precise economic interpretation, while a wide interval should prevent a confident conclusion, even if the point estimate looks large. We can decompose variation in y into an explained part and a residual part. The total sum of squares adds the squared distances from observed y to its sample mean. The explained sum adds the squared distances from fitted y to that mean. The residual sum adds the squared residuals. With an intercept, total variation equals explained variation plus residual variation. R squared is the explained sum of squares divided by the total sum of squares. Equivalently, it is 1 minus the residual sum divided by the total sum. It measures the fraction of sample variation in y, represented by the fitted values. A value near 1 signals a close-in sample fit, while a value near 0 signals little explained variation. R squared is not a measure of causality, unbiasedness, or correct specification. A high value can arise from common trends, excessive flexibility, or a few influential observations. A low value can still accompany a well-identified and economically important coefficient. The appropriate standard for fit depends on the question, data frequency, and variability of the outcome. Now consider the built-in R data on 32 cars. We regress fuel efficiency, measured in miles per gallon, on vehicle weight, measured in thousands of pounds. The estimated slope is about negative 5.34. Within this sample, an additional 1,000 pounds of weight is associated with roughly 5.3 fewer miles per gallon on average. The slope t statistic is about negative 9.56 with an extremely small p-value. R squared is about 0.75, so weight alone represents about 3/4 of the sample variation in fuel efficiency. The residual standard error is about 3.05 miles per gallon. These values describe this model and sample, not a universal engineering law. The scatter plot shows a clear negative relationship and lets us inspect whether a line is plausible. The analysis of variance reaches the same overall conclusion. Its F statistic is about 91.4, comparing explained variation per slope with unexplained variation per residual degree of freedom. In a simple regression, this F statistic equals the square of the slope t statistic. Numerical output cannot replace the plot. We should look for curvature, changing spread, clusters, and observations with unusual x values. A single high-leverage car can rotate a fitted line even when its residual is modest. Residual plots and influence measures help distinguish a stable sample relationship from one that depends on a small part of the data. The case study also illustrates a disciplined interpretation. Weight is a strong predictor of fuel efficiency in these data, but vehicle design, engine power, transmission, and other features are omitted. We should inspect those channels before making a causal statement. The next lesson extends the model so several explanatory variables can enter together. Simple regression is useful for intuition, but economic outcomes rarely have only one relevant predictor. Multiple regression includes several explanatory variables at once. It lets us ask how an outcome changes with one regressor while holding the others fixed. This all-else equal interpretation is central in labor economics, macroeconomics, finance, public policy, and many other applied fields. Imagine a wage equation containing education, experience, region, and demographic controls. The education coefficient compares observations with the same included values of the other regressors. That conditional comparison is more informative than a raw education-wage correlation. It is still not automatically causal, because unobserved determinants can remain in the error. With k regressors, we say that y equals beta 0 plus beta 1 times x1, continuing through beta k times xk plus u. Beta j measures the change in the conditional expected value of y associated with a 1-unit increase in xj, holding every other included regressor fixed. The intercept refers to all regressors being 0, which may lie outside a meaningful data range. The phrase holding other regressors fixed describes a partial relationship. Conceptually, we remove from xj the part predicted by the remaining regressors, and we ask whether the remaining variation in xj moves with the remaining variation in y. If little independent variation remains, the partial effect will be imprecise, even when the variables are strongly correlated in raw data. OLS extends directly to this setting. For every observation, the fitted value combines the estimated intercept and all estimated slopes. The residual is observed y minus the fitted value. We choose the full coefficient vector to minimize the sum of squared residuals over the sample. The first-order conditions are called the normal equations. They require residuals to sum to 0 when an intercept is present, and require each regressor to be orthogonal to the residuals. There is one equation for each estimated coefficient. A unique solution requires that no regressor be an exact linear combination of the others. Matrix notation makes the structure compact. We stack the outcomes into a vector called y, the regressors into a matrix called x, the coefficients into a vector called beta, and the errors into a vector called u. The model becomes y equals x beta plus u. The first column of x is a column of 1s when the model includes an intercept. The matrix OLS estimator is spoken as follows. Beta hat equals the inverse of x transpose x multiplied by x transpose y. This expression exists when x has full column rank, so x transpose x is invertible. The formula is computationally convenient and also reveals how the geometry of the regressor matrix determines the precision of coefficient estimates. The Gauss-Markov conditions describe when ordinary least squares behaves well, and there are 4 of them. First, the model is linear in its parameters. Second, the regressor matrix has full column rank. Third, given the regressors, the errors have mean 0. And fourth, given the regressors, every error has the same variance and no error is correlated with another. Notice that none of these conditions say anything yet about a normal distribution. Normality is not part of the Gauss-Markov theorem itself. It is an additional condition used to obtain exact small sample T and F distributions. Under the core Gauss-Markov assumptions, OLS is already linear and unbiased, and its covariance matrix equals sigma squared times the inverse of x transpose x. The theorem says that OLS is the best linear unbiased estimator, often called the blue estimator. Best has a precise meaning. Among estimators that are linear functions of y and unbiased for beta, none has a smaller covariance matrix. It does not mean that OLS dominates every nonlinear or biased estimator under every loss function. Efficiency depends on the covariance assumption. If errors have different variances or are correlated, the usual OLS estimator may remain unbiased under exogeneity, but the Gauss-Markov efficiency claim no longer holds. Its conventional standard errors may also be wrong. We will study that distinction carefully when we turn to heteroskedasticity. For one coefficient, a two-sided t-test compares the null that beta j equals a proposed value with the alternative that it differs. The t statistic is beta j hat minus the proposed value divided by the estimated standard error of beta j hat. Under classical normal errors, it follows a t-distribution with the sample size minus k minus 1 degrees of freedom. A one-sided test uses the same statistic but a directional alternative. The direction must come from the research question before inspecting the estimate. Choosing a one-sided alternative only after seeing the sign invalidates the intended error probability. We should also report confidence intervals and economic magnitudes rather than reducing inference to a significance label. Many economic hypotheses restrict several coefficients jointly. We may ask whether all factor exposures are zero, whether two policy effects are equal, or whether a weighted combination equals a theoretical value. An F-test compares a restricted model that imposes the null with an unrestricted model that does not. A sequence of separate t-tests is not generally equivalent to one joint F-test. Several coefficients can be individually uncertain, yet jointly important because their estimates are correlated. Conversely, repeated individual testing raises the chance of at least one accidental rejection. The joint test should match the economic hypothesis rather than serve as a search for significance. The general F statistic measures the increase in the residual sum of squares caused by the restrictions divided by the number of restrictions. It then scales this increase by the unrestricted residual variance estimate. A large value means that imposing the restrictions worsens fit by more than we would expect from sampling noise under the null. The overall F-test asks whether all slope coefficients are jointly zero. The restricted model then contains only an intercept. Its residual sum of squares equals the total sum of squares from the unrestricted sample. The test compares explained variation per slope with residual variation per remaining degree of freedom. R squared and the overall F statistic are algebraically related. For a fixed sample size and fixed number of regressors, a larger R squared produces a larger overall F statistic. Their interpretations differ, however. R squared describes the fraction of sample variation explained, while the F-test evaluates a probabilistic null hypothesis under specified assumptions. Adding a regressor can never reduce ordinary R squared, even if the variable has no real explanatory content. Adjusted R squared corrects for this mechanical advantage by comparing residual variation and total variation after their respective degrees of freedom adjustments. It can fall when an added regressor contributes too little. The residual standard error estimates the common error standard deviation under homoskedasticity. It is the square root of the residual sum of squares divided by the sample size minus the number of estimated parameters. Unlike R squared, it is expressed in the units of y, so it describes a typical residual scale that can be compared with economically meaningful magnitudes. No single fit measure chooses a model for us. Adjusted R squared does not validate exogeneity, guarantee stable prediction, or justify a complicated specification. We must combine theory, data design, coefficient interpretation, residual diagnostics, and out-of-sample performance when relevant. The next lessons examine two threats that a polished regression table can hide. The classical regression model assumes that the conditional variance of the error is constant across observations. Heteroskedasticity means that this variance changes with one or more regressors. The conditional mean may still be correctly specified, yet the cloud of outcomes can be narrow for some observations and wide for others. This pattern is common in cross-sectional economics. Larger firms can have more variable profits than smaller firms. Higher income households can display a wider range of expenditure. Countries of different sizes may have very different shock magnitudes. Heteroskedasticity can also signal an omitted variable, an inappropriate functional form, or a structural change. Under zero-conditional mean, heteroskedasticity does not by itself bias the OLS coefficient estimates. They remain unbiased and consistent under the usual regularity conditions. The problem is precision. OLS is no longer guaranteed to be the most efficient, linear, unbiased estimator, and the conventional homoskedastic standard error formula is generally incorrect. Incorrect standard errors contaminate confidence intervals, t-tests, and f-tests. If the conventional formula understates uncertainty, we may declare effects significant too often. If it overstates uncertainty, we may overlook useful evidence. The direction is not known in advance, so the fact that coefficients appear plausible is not a defense against a variance problem. In simple regression, the heteroskedastic variance of the slope depends on a weighted sum of observation-specific error variances. Observations whose x values are far from the sample mean receive greater leverage in that expression. If those influential observations also have high error variance, the slope can be much less precise than the homoskedastic formula suggests. The intercept variance changes as well. Both exact heteroskedastic variance expressions contain unknown observation-specific variances, so we cannot calculate them directly. This motivates two broad responses. We can estimate a covariance matrix that is robust to an unknown variance pattern, or we can specify and estimate a variance model for generalized least squares. A normal-looking residual histogram does not establish homoskedasticity. The histogram combines observations across all fitted values and describes a marginal distribution. Heteroskedasticity is a conditional statement. Residuals may look approximately bell-shaped overall, while their spread grows sharply with X or with the fitted outcome. This distinction is visible in a residual versus fitted plot. A fan or funnel shape suggests changing conditional variance. A plot can also reveal curvature, clusters, or influential observations. Graphical evidence is valuable because a formal test compresses a pattern into one statistic and may miss a form of heteroskedasticity that was not specified. A synthetic example can preserve a roughly bell-shaped collection of shocks while arranging larger shocks at larger values of X. The residual histogram remains familiar, but the residual versus fitted plot widens. The lesson is not that every fan proves heteroskedasticity. Rather, we should inspect conditional spread instead of relying on an unconditional normality check. The Engel household data provide an economic example. Food expenditure rises with household income, and the dispersion of expenditure around the fitted line also becomes larger at higher income. A simple conditional mean may describe the average relationship reasonably well, while a constant variance assumption fails visibly. Formal tests begin with the OLS residuals from the original mean model. Many then use squared residuals as proxies for unobserved error variances. An auxiliary regression asks whether those squared residuals are systematically related to selected variance drivers. The test is therefore only as informative as its assumptions and chosen drivers. The Broich PAI's gun test specifies variables that may explain the variance. Under the null hypothesis, their non-constant variance coefficients are all zero. Under the alternative, at least one is not zero. The variance drivers may be the original regressors or other variables justified by the economic setting. To implement the test, first estimate the original regression and save its residuals. Second, regress squared residuals on a constant and the selected variance drivers. Third, multiply the auxiliary r squared by the sample size. In a large sample under the null, this statistic has a chi-squared reference distribution, with degrees of freedom equal to the number of non-constant drivers. The Broich-Peillat-Gunn procedure is called a Lagrange multiplier test because it asks whether relaxing the homoskedastic restrictions would improve the likelihood. Its convenient sample size times r squared form is an asymptotic result. In a small sample, the approximation and the sensitivity to unusual observations deserve caution. The White test uses a more flexible auxiliary regression. With two original regressors, it can include those regressors, their squares, and their cross product. The statistic again uses the sample size times auxiliary r squared. This flexibility can detect many variance patterns without selecting one narrow functional form. Flexibility also has a cost. Squares and interactions consume degrees of freedom, can become highly collinear, and may overfit a small sample. A rejection indicates non-constant variance, but does not identify a correct variance model. A failure to reject is not proof of homoskedasticity, especially when the test has low power. The Goldfeld quant test is designed for variance differences across groups or along a scale variable. We order observations by a suspected scale variable, often remove a middle block, estimate separate regressions for low and high groups, and compare their residual variance estimates through an F ratio. Removing middle observations sharpens the contrast between groups, but reduces the sample and degrees of freedom. A directional test should be used only when theory predicts which group has larger variance. If the groups are labelled after observing their estimated variances, the reference rule must account for that data-dependent choice. Formal tests have size and power trade-offs. A highly flexible test may detect many patterns but estimate too many auxiliary coefficients for the available sample. A narrow test can be powerful against its chosen alternative and blind to others. Report the precise auxiliary specification, not merely the name of the test and a p-value. Squared residuals are noisy proxies for squared errors, particularly at high leverage observations. Some finite sample procedures adjust for leverage before constructing a diagnostic. This is another reason to compare formal results with plots and subject matter knowledge, instead of treating sample size times auxiliary r squared as a direct observation of the variance function. Testing the variance does not rescue a misspecified conditional mean. Curvature omitted from the mean can create a patterned residual spread and trigger heteroskedasticity tests. Before selecting a correction, ask whether the residual plot suggests changing variance, missing non-linearity, omitted groups, or several problems at once. It is also unnecessary to earn permission for robust standard errors through a preliminary rejection. A pretest can add instability because the final method changes according to a noisy p-value. When heteroskedasticity is plausible, reporting a suitable robust covariance estimate alongside transparent diagnostics is often a sensible default. Sample size changes how we read the evidence. In a small sample, a visually suggestive pattern may not produce a small p-value, while a very large sample may reject a mild and economically unimportant departure. We should describe the pattern's magnitude and practical consequence, not only whether a test crosses a conventional threshold, so no single test settles this on its own. What I want you to take away is that a good analysis combines residual plots, economic reasoning, and tests aimed at the patterns you actually expect, and keep detection separate from correction. When we reject constant variance, that tells us our usual standard errors need attention, but it does not tell us which weighted model is the right one. That is exactly the question we take up in the next lesson. Once heteroskedasticity is credible, we face two separate questions. How should we conduct inference, and can we estimate the coefficients more efficiently? Robust standard errors answer the first question while keeping the OLS coefficients. Generalized least squares addresses the second by weighting observations according to a variance model. White's heteroskedasticity, consistent covariance estimator, replaces unknown observation-specific error variances with functions of squared OLS residuals. In matrix language, the estimator has a sandwich form. The outer pieces reflect the regressor geometry, while the middle piece lets residual variation differ across observations. Several finite sample versions are labeled HC0 through HC3 and beyond. Here, HC stands for heteroskedasticity consistent. These versions share the same large sample objective, but adjust residual contributions differently. HC1 applies a degrees of freedom correction. HC2 and HC3 account more directly for leverage, with HC3 often used as a cautious choice in smaller samples. Robust standard errors leave fitted values, residuals, and coefficient estimates unchanged. They change the estimated uncertainty around those coefficients. A robust t-statistic divides a coefficient estimate by its robust standard error. This repairs inference asymptotically under general heteroskedasticity, provided the conditional mean and sampling conditions remain appropriate. Robust does not mean assumption-free. These formulas do not correct omitted variable bias, reverse causality, dependence across observations, or a poor functional form. They may perform imperfectly in a very small sample. If errors are clustered or serially correlated, we need covariance estimators designed for those dependence patterns. Robust covariance estimates also support confidence intervals and joint-walled tests. The coefficient restriction remains the same, but the covariance matrix used to measure its uncertainty changes. Software options should be recorded carefully because a default homoskedastic covariance, an HC correction, and a clustered covariance can produce materially different conclusions from identical coefficient estimates. Generalized least squares, or GLS, uses more structure. Suppose the error variance is proportional to a known positive quantity for each observation. We divide the outcome and every regressor, including the intercept column, by the square root of that quantity. The transformed error then has constant variance. Applying OLS to the transformed equation is equivalent to weighted least squares in the original equation. Observations with larger error variance receive smaller weight because they contain less precise information about the conditional mean. When the variance model is correct, GLS can estimate beta more efficiently than unweighted OLS. Weights must be proportional to inverse variance, not inverse standard deviation, in the weighted least squares objective. Dividing each equation by its error, standard deviation produces precisely those inverse variance weights after squaring. Confusing variance with standard deviation is a small-looking coding choice that estimates the wrong criterion. The intercept needs special attention after transformation. Dividing an equation by a scale factor turns the original constant into a transformed regressor equal to 1 divided by that factor. Running an ordinary regression with a new untransformed intercept would estimate a different model. This is a frequent implementation error. In most applications, the variance function is unknown. Feasible generalized least squares, or FGLS, estimates it. One common model says that error variance is proportional to x raised to an unknown power. Taking logarithms turns this into a linear relation between log variance and log x. The feasible procedure begins with OLS. We regress the logarithm of squared residuals on a constant and the proposed log variance drivers. Because a residual can be zero or extremely small, computation needs a safe lower bound before taking logarithms. The fitted auxiliary values are then transformed back into positive estimated variances. Next, divide the outcome and all regressors by the estimated error, standard deviation, and run OLS on the transformed data. The resulting estimator is feasible because the weights have been estimated rather than known. Under a correctly specified variance model, it can be asymptotically more efficient than OLS. Because the weights are estimated, the second stage should not be described as if an oracle supplied them. Large sample theory can account for this first stage under suitable conditions, but small sample performance depends on both regressions. Inspect fitted variances for extreme weights that could allow a few observations to dominate. A misspecified variance model can remove the promised efficiency gain and may make results worse. For this reason, robust OLS often provides a reliable baseline, while FGLS serves as a model-based refinement and sensitivity check. Agreement is reassuring. A large disagreement calls for renewed scrutiny of both the mean and variance specifications. Return to the Engel food expenditure regression. The OLS intercept is about 147.5, and the income slope is about 0.485. Income explains a large share of expenditure variation, but both Broich-Pagan and White tests strongly reject constant variance. The HC1 robust standard error for the intercept rises from about 16 to about 46.6. The slope standard error rises from about 0.014 to about 0.052. The point estimates do not move, but the uncertainty is much larger than conventional OLS suggests. A GLS specification that makes variance proportional to income produces a slope near 0.54. An estimated variance model produces an FGLS slope near 0.57. These differences remind us that weighting changes the criterion and can change point estimates, not merely their reported standard errors. Fit measures from a weighted regression live on a transformed scale. Its R squared and residual standard error should not be compared mechanically with their unweighted counterparts. A smaller transformed residual standard error does not automatically mean a better fit in the original units of food expenditure. The wage case study illustrates group-wise variance. Wages are regressed on education and experience, and separate residual variances are calculated for men and women. The variance ratio is about 1.22, with a two-sided p-value near 0.10. This is suggestive, but not strong evidence at the conventional 5% level. Group-wise, FGLS assigns each observation a weight based on its group's estimated residual variance. In this example, coefficients remain close to OLS, and standard errors change only slightly. That modest result is informative. A sophisticated correction should not be expected to transform a data pattern that the diagnostic evidence itself describes as weak. An informative results table can present OLS coefficients once and place conventional and robust standard errors beside them, followed by a clearly labelled weighted estimate when justified. State the variance model, the HC version, and the scale of each fit measure. This makes the sensitivity analysis auditable and prevents different estimators from being mistaken for cosmetic formatting choices. If you remember one rule from this lesson, let it be this: keep robust inference separate from efficiency modeling. When heteroskedasticity is plausible, report ordinary least squares together with a suitable robust covariance estimate. Reach for generalized or feasible generalized least squares only when a variance structure has real economic justification and survives your diagnostic checks, and never present estimated weights as if they were known facts. Multicollinearity describes exact or near linear relationships among explanatory variables. In matrix terms, columns of the regressor matrix are linearly dependent or nearly dependent. The issue arises because multiple regression tries to separate effects by comparing changes in one regressor while holding the others fixed. That comparison becomes difficult when the data rarely provide such independent movement. Exact multicollinearity means that one regressor is an exact linear combination of others, including an intercept. A male indicator and its female complement is one example, including two components, and their exact total is another. The regressor cross-product matrix is then singular. So the normal equations do not have a unique coefficient solution. The separate effects cannot be recovered from that parameterization. Software commonly responds by dropping a perfectly collinear column. This is a computational necessity, not a scientific decision about which variable belongs in the model. The researcher must identify the redundant representation and choose a parameterization that preserves the economic question. Otherwise, the reported reference category or coefficient interpretation may change without being noticed. Approximate multicollinearity is less obvious. The regressor matrix remains invertible, but one or more eigenvalues are very small. OLS exists, yet the inverse magnifies sampling noise in the weakly identified directions. Small changes to observations or specification can then produce large coefficient movements or sign reversals. Under homoskedasticity, the covariance matrix of beta hat equals sigma squared times the inverse of x transpose x. Highly correlated regressors make relevant diagonal elements of that inverse large. Standard errors rise because the data do not clearly distinguish the separate all-else-equal effects of variables that move together. A characteristic pattern is a high R squared and a significant overall F test alongside weak individual T statistics. The regressors may collectively explain why, while their individual contributions remain hard to separate. This pattern can suggest multicollinearity, but it is not sufficient by itself because weak T statistics have many other causes. For two standardized regressors, the variance inflation for one coefficient is related to 1 divided by 1 minus the squared correlation between them. As the absolute correlation approaches 1, the denominator approaches 0 and the coefficient variance grows rapidly. With many regressors, small eigenvalues generalize this same geometric idea. A correlation matrix is a useful first screen. Large pairwise correlations reveal obvious overlap between two regressors. Its limitation is equally important. A variable can be nearly explained by a combination of 3 or more variables, even when no pairwise correlation appears extreme. Pairwise inspection is therefore a beginning, not a complete diagnosis. The variance inflation factor examines each regressor against all the others. Regress xj on the remaining regressors and record r squared from that auxiliary regression. The variance inflation factor equals 1 divided by the quantity 1 minus that r squared. A value of 1 means no linear predictability from the other regressors. Large variance inflation factors signal that an individual coefficient is being estimated from little independent variation. Thresholds, such as 5 or 10, are only rough conventions. The consequences depend on sample size, measurement quality, the coefficient combination of interest, and whether the goal is structural interpretation or prediction. Condition indices examine the full regressor system after appropriate centering and scaling. We compare the largest eigenvalue with each smaller eigenvalue. The overall condition number is the square root of the largest eigenvalue divided by the smallest. A value above 10 may indicate moderate collinearity, while much larger values suggest serious numerical fragility. Scaling matters because a raw condition number can be dominated by units rather than true dependence. A variable measured in dollars and another measured in millions of dollars can create poor numerical conditioning without changing substantive information. Centering and scaling make the diagnostic more interpretable, but they do not create independent variation that the sample lacks. Variance decomposition proportions can show which coefficients draw much of their uncertainty from the same small eigenvalue direction. This identifies groups of variables that are jointly entangled. Sensitivity checks add practical evidence by tracking coefficients when related regressors are removed, variables are transformed, or a few observations are changed. Centering is particularly useful when a model includes powers or interactions. Replacing x and x squared with centered x and centered x squared can reduce non-essential correlation and improve the intercept's meaning. It does not cure collinearity created by genuinely similar economic variables that move together. We can sometimes redefine or combine variables. Near duplicate measures may be replaced by one well-motivated index, a spread, a ratio, or a factor. This trades a set of fragile individual effects for a smaller number of more stable combinations. The choice must follow the research question rather than an automatic diagnostic threshold. Credible theory can supply coefficient restrictions or informative priors. Restricted least squares and Bayesian methods reduce effective dimensionality, but their apparent precision depends on the validity of the restrictions. A convenient restriction imposed only to obtain significance can conceal rather than solve an identification problem. Regularization deliberately accepts a little bias in exchange for lower variance. Ridge regression shrinks correlated coefficients towards zero and steadies the matrix inversion. Lasso and elastic net go further and drop some variables as they shrink. Principal components regression rebuilds the regressors as orthogonal combinations and can set aside the directions tied to the smallest eigenvalues. Whichever method we use, the amount of shrinkage has to be chosen with an honest validation procedure, not by eye. These methods are valuable for prediction, especially with many predictors, but their coefficients answer different questions from unrestricted OLS. Variable selection among a cluster of correlated regressors can be unstable. If the goal is a causal effect for one original variable, regularization does not manufacture the missing independent variation. The most direct remedy is often better data. We want observations in which the regressors vary more independently, perhaps through a broader sample, an experiment, a quasi-experiment, or improved measurement. No algebraic transformation can fully separate effects that the observed data never distinguish. Identification ultimately comes from variation, not from a diagnostic command. Now consider the multivariate fuel efficiency model. Miles per gallon is explained using weight, horsepower, displacement, axle ratio, quarter-mile time, cylinders, and transmission. The model has R squared near 0.88 and adjusted R² near 0.83, with a significant overall F-test. The adjusted generalized variance inflation measures are roughly between 1.8 and 3.7, and the scaled condition number is about 10.2. These diagnostics indicate moderate, not extreme, multicollinearity. Size and power measures move together, so individual slopes are less precise, even though the model explains fuel efficiency well as a group. Heteroskedasticity tests give mixed evidence in this case. A simple Broich-Pay gun specification does not reject at 5%, while a richer variance specification does. The heteroskedasticity consistent type 3 correction, usually called HC3, leaves the coefficient estimates unchanged, but changes the estimated uncertainty around them. Under that robust analysis, vehicle weight remains the clearest individually significant predictor. Functional form and influence checks complete the picture. A Ramsey test provides no strong evidence against the chosen functional form. Residual and leverage plots identify a few cars worth examining, while correlations confirm that displacement, weight, and related size measures move closely together. No single observation or diagnostic should be allowed to dictate the conclusion. This chapter's central message is that estimation begins rather than ends the analysis. OLS provides a transparent benchmark. Tests and fit measures quantify selected features under assumptions. Heteroskedasticity and multicollinearity show how a good-looking fit can hide fragile inference. Reliable work combines economic design, visual checks, robust uncertainty, sensitivity analysis, and clear limits on interpretation.